So now we did two examples, actually two big examples on MIMO system, and we saw it is similar to the analysis we did in CISO system in the lecture. Just you need to pay attention to your dimensions. And also we learned that we can do it on control system tuner app without using place. And control system tuner app is using an iteration way, an optimal control way, in order to reach the goal. So then you get better performance than having your own design goal, like saying that's my closed loop desired location of my poles and can computing K. So then it is better than control tuner app. But if you want to know the theory behind it, how it is done, this iteration, this optimization process, we'll learn it at the end of this lecture. But for now we are fine with this. So, and we did two exercises, and this particular exercise in MIMO system was type 0 system. But if it is type 1, nothing will change. So just we need to do it as we did for the CISO system and get inspired from everything we did here. Well, I didn't find for now a type 1 MIMO system. I will ignore the fact that the helicopter is a type 0, and I do it as if it is type 1. And this is remind you of your exercise we did here on type 1 system, and on type 0 system, sorry. And when we said let's ignore the fact that the system is type 0 and work with it as if it is type 1, as if it's type 1 system. Therefore, I may work on it as it is like this. Okay. So if I'm feeding it this way, so let's do it on MATLAB. How this will be. Alright, so look at it again. Now I'm ignoring the fact that it is type 0 system, considering it's a type 1, and I will study it as if it's type 1. We know it is wrong, but just for the sake of practicing a type 1 system. So what you feed back is whatever you are not going to control. Everything you want to control, you don't feed it back. And the K that you put it here are the K corresponding to whatever you want to control. So then, all what you need to do in control system tuner app is to know the K. Here is the key point, right? So, I'm not considering 8 states now because I explained to you what they did here, and some of the states are stable, some because of the sensors they have, etc. And we found we get same answers. So I will take the 5 state here. So I have 5 just output. So I keep C measure inside the state space representation block. And then what is K here in this case? So it's not K hat, it's K. So I have 5 states, and I have U1, U2, U3. So then it is 5, it's a 3, 5 system. So what do I have inside? I should have whatever I want to control is in a place, and whatever I don't want to control and in the other place. Well, we want to control the first 3. The first 3, K11, K12, K13, K31, so here K21, K22, K23. Okay, etc. You have up to actually K14 and K15. That's it. 24, K25, K34, and K35. That's your system. So then, here is what you want to control. So it's a 3 by 3 matrix. So then this will go to the forward loop. So if you look to your lecture, This is what you want to control, so you will put it here, 3 by 3 matrix. And what you want to put it here is the remaining two states. So this corresponds to actually, if you wish, to x4, x7, and x8, what you want to control. And here is 3 by 2 matrix, and this is corresponds to x3 and x6. So I will go and put zeros here, 3 by 3, and here 3 by 2 in the feedback loop. So 3 by 2 in the feedback loop. It's tuned now, but it was 0. And here it's 3 by 3. Okay? And only I get the states, the last 2 states. The first 3 states, I take them directly to here. I feed them. Okay, here I put a multiplexer just to combine the signal together. It's alright. And here actually it is not phi. Well, if you want the correct name here is phi. I combine them all in one step. Phi, theta, if you wish. Theta, phi, and r. They are all in one state. In one, so you see, at time 3 you have one step, at time 0 you have another step, at time 6 you have another step. So corresponds to whatever you have. So then that's your system will look like this. We know it is wrong because it's not a system of type 1, but just for your, just to be able to see how easy it is then. And your tuning goal, I get same tuning goal as before, and that's what I get. Okay, it seems better than before. What do you think? Let's compare it. We know that up to now all the systems, my architects, 3 state, 8 state, all they get same values. So then, what now? It looks like here it has a better control. See how it is for the same design goal. It seems like here I have better achievement, right? So what's going on here? Well, I have good tracking. I have a good tracking, and the integrator role is to have good tracking. But if you want in practice, this system doesn't really need good tracking because yeah, sorry, it's a bit slow. Because if you look to the state, well, many of them are close to 0. So somehow they don't need an integrator because it's close to the imaginary axis. Get the point? So then tracking is okay. So then do I consider it this way? We said this wrong. Well, actually it is not recommended to take it as a system of type 1. Should keep it system type 0, because let's look at the control effort here, and the control effort, for example, in here, in here. All right. So now we can understand why it's not recommended to go this way. For example, you can see here up to 500, up to 100, etc. Depends. So you have 4 signals. So then you will. It's not good for your actuator. So in order to have this stability, you need to have a good control effort, which is not the case here. Even so, I'm saying I'm applying the same control goal to achieve the on control system tuner app. I'm taking the same design goal for all. So you see the control effort here is much better. So then that's why not recommended to consider it for that type of system, but for other system, it's a really type 1. You go over it, and so now you know how to go on it easily. So now, from now, if you wish, you don't really need to do place and so on. Do it on control system tuner app. Okay. What about the control effort here? Well, here and there, the only change is in Just I'm taking off the roll of filters, and I'm having 5 state instead of 8. Sorry, no, I don't want to look to the output, I want to look to the control effort. And control effort here. Good. So here for this, so the one with the roll off filter is a bit smoother, a bit better. Well, here up to 0.2, here up to, but overall same, because I have same response. So here it's a bit smoother when I have the roll off filter. Okay, what if I compare it with the original system? Control effort for the original system. MATLAB did. Well, happy to know that your system, guys, is better. Slightly better, right? It's the same 10, but at least here you can have a peak of 0.4, a bit more here, a peak of 0.1, etc. Good. So now that's it. You know everything for in simulation. You can control any MIMO system, whatever number of input and output. You can do state space controller for it. So if you go to your now, of course you can go to your tutorial. You have it. This is the helicopter actually. Let's see how they did, the design goal we took, etc. Of course. You can take any MIMO system, like the one you did in your exam, for example. Yeah, that's the one you did in your exam, right? For example, in the, not exactly in your exam, in the bonus exam, for example, 6 input, 6 output, you can even, so you do it with state space controller. You have 6 input, 6 output, so you can also do it, and exactly same way. Good. And look to the performance. You can have a comparison between state space and PID. That's it for the simulation part. So next time we'll start talking about some problems that you may meet in the experimental implementation. When you go to the experimental implementation, so then in this case you may need actually to state observers if you have lack of the number of sensors, or you cannot measure all the states. We'll talk in details about it next week.